Hello everyone. In this video, we are going to discuss the difference between an ideal dipole and a real dipole. First, let us try to understand what is a dipole. If you take a hydrogen atom and a chlorine atom, then it will consist of a nucleus and an electron cloud. Now, this hydrogen atom and chlorine atom, they are separated from each other. If I bring them closer, there will be a distortion of the electron cloud due to the difference in electronegativity. Now, because of this distortion, the hydrogen atom will have a positive polarity and the chlorine atom will have a negative polarity. Now, this delta plus and delta minus, they are of equal magnitude but different polarities. Such type of system is what we call as the electric dipole. And please note here that when we are dealing with this kind of real atoms, the electron cloud, it is not a point, rather it's a distribution which is governed by the quantum mechanics. Now, there is a simple representation of such type of system. Here, we represent the electric dipole by two equal and opposite charges separated by some distance t. Now, if you want to find out the electric field or electric potential at a particular point P, then we have to use certain techniques. But the electric field, it's a vector quantity, so we need to find out the three components. Whereas electric potential, it's a scalar quantity, so we have to find out only a single component. Finding out electric potential is relatively easy compared to electric field. Once we get the electric potential, we can find out the electric field using this relation. Now, while calculating the potential of a dipole, we can consider two regimes. One is the near field, the other one is the far field. In the near field calculation, we are interested to find the electric potential at a point nearby the dipole. Now we can represent R plus as the distance of the positive charge from point P and R minus as the distance from negative charge. And since the electric potential is a scalar quantity, we can just take the sum of V plus and V minus to get the total potential. Now this V plus and V minus, we can use the formula of a potential due to a point charge, and these are the formulas. Then we can substitute this to expression and we can get the final expression of the potential. Now, if you want to find out the electric field, we can use this relation and we can find out the electric field also. Now, we can calculate the electric field or electric potential in the near field region. We can use the Coulomb's law also. But the thing is, we do not get any neat or simplified expression when we are dealing with at a point near the dipole. The closer we go to the dipole, the more complex the expression will be. Using the near field calculation, which we have done just now, we can plot the electric field lines for this dipole, and the electric field lines will look like this. In the far field calculation, we are interested in finding the electric potential or electric field at a point which is very far away from the dipole. The far field calculation, we can use the multipole expansion. By the way, I have released a video on multipole expansion. If you're interested, you can go and watch the video. In multipole expansion, the electric potential is expressed as a contribution from different terms. The first one is the monopole, second term is the dipole contribution, third term is the quadrupole, and then we have octapole, and this series goes on. Now, if we look into the R dependence from this term, then it will look like this. So as we go to higher pole terms, the contribution will become lesser and lesser because the power of R is increasing and it is in the denominator. Let us discuss this monopole term. So the monopole term, it depends on 1 by r and the net charge. So for electric dipole, since it has plus q and minus q, the net charge will be 0. So the monopole contribution will be 0. What about the dipole term? The dipole term depends on 1 by r square and the dot product of the dipole moment and the unit vector of the position. Now, if the dipole moment here, for the dipole moment, its magnitude is q into d, and if p vector is not perpendicular to the r cap, then the dipole contribution will be non-zero, and under that condition, we can approximate the potential as equal to the potential of a dipole. Now, this approximation becomes better and better if we take the point very far away from the dipole. Let us compare the electric field pattern for the near field calculation and the far field calculation. So for the near field, we have this electric dipole, and we can plot the electric field lines, and the field lines will look like this. But for the far field calculation, we are calculating the electric field lines at a point which is very far away from the dipole, and the field pattern will look like this. Now you can see the difference between these two field patterns. And as we go very far away from the electric dipole, the field pattern will be much different from the near field calculation. Now, let us summarize what we have done so far. In the near field calculation, when we are given a dipole, we were calculating the electric potential or electric field at a point nearby the dipole. And this is what we call as the real dipole, or sometimes it is known as the physical dipole. In the case of far field calculation, we were calculating the electric potential or electric field at a point which is very far away from the dipole, or we can say r much greater than the d, where d is the separation between the two charges. Now when d is very small, or when d tends to 0, the dipole moment will also tend to 0, because dipole moment magnitude is given by q into d. But dipole moment cannot be 0, because we are approximating the potential with the dipole potential. So in that case, we have to choose a condition such that when d is tending to 0, the dipole moment should be finite instead of going to 0. So these two cases, that is r much greater than d, or d tending to 0 and the dipole moment is finite, in that case, the dipole we refer to as the ideal dipole. Thank you everyone for watching.